So welcome everybody. As Sebastian has just introduced, today in particular in my lecture we will be talking primarily about ab initio thermodynamics. This is now starting to become different than the tutorials that you have heard up to now in this series, which were completely focused on the electronic structure part. And now we're moving away from the electronic structure, first principles regime, into combining it with other methods as part of first steps of a multi-scale modeling kind of idea. To motivate why this is necessary, let me use the area of heterogeneous catalysis, or more generally, the area of energy conversion technologies like solar cells, batteries, electrocatalysis, thermal catalysis, photocatalysis, etc. And basically what they all have in common is that I would like to first tell you that we need to sort of like extend the predictive realm of quantum chemistry that you have met up to now in this tutorial series. So there's a number of energy conversion strategies that we have to further develop to eventually arrive at a sustainable energy provision for our society. Starting from sunlight, we need to convert that energy in terms of photons into electricity or in terms of fuels. And we need to store the electricity either in fuels or in batteries. And then eventually we will have to recover everything for the different needs that we have in our society. This is all very diverse kind of applications, and also the research communities that work on these different areas are quite different. They have quite some commonalities. One commonality of them, which is sort of like very obvious, is that most of the limitations that we're currently seeing in these different technologies arise at interfaces. And that I would like to just illustrate or show you here. One of the general problems that we have with these interfaces is that they're so-called working. So it's not like we're designing a material and then cut it, for example, to create a surface, and then that sort of like originally designed and created surface would be the one that is really doing the job. Rather, what is evolving is that somehow as a function of the operating conditions, for example, here in thermal catalysis, this is a nanoparticle on stream that you see here. These surfaces of these catalysts undergo some hitherto typically not sufficiently characterized morphological, structural, and compositional evolution to sort of like evolve into the truly active. This is not only so in surfaces in the catalytic context, but for example, we have it in batteries too. There we call these things solid electrolyte interfaces, or even between different crystalline grain boundaries in solid state batteries, for example. At these interfaces, there are extended interfaces with pH, so extended objects that really are the ones where we have the problems and the limitations in terms of both ionic and electronic charge conductivity. We don't really fully understand the mechanisms as they work, in particular, for example, in terms of charge transport, but also in terms of like electrocatalytic kind of reactions. We typically don't understand the influence of the environment. So in electrocatalysis, for example, the influence of the surrounding electrolyte, the operating conditions in thermal catalysis, so temperature and pressure, or in, of course, the applied potential in anything that's involving electron. And last not least, on a very fundamental level, we're even not so sure about the degree of adiabaticity that each of these individual elementary processes actually. And the big problem that we have is that interfaces by themselves or surfaces require very large, even supercells, if we want to describe them at the electronic structure level. We would typically periodic boundary condition codes devise slab models. So we would create a finite number of layers and then put that into a big supercell in order to create a surface, for example. And these are very large calculations, but even these kinds of calculations do not bring us really into this size range that we would need to do here, both in terms of really the absolute size of the system, but also because very often we now require statistics. We need to do ensemble averages. We need to follow time evolutions of systems. We need to sample many different possibilities. And this means that we have to do calculations over and over and over again. And even if we could, for example, on a DFT level, do one calculation, yes, more or less, we would not be able to do it a zillion times in order to really get to the right kind of ensemble treatments. That is, in a sense, the motivation why, in principle, need to come up with a different approach. We have, sort of like with electronic structure theories, like density functional theory, a method that describes the electronic regime quite well. Capable supercomputers, we might actually extend it even a little bit into the atomistic regime, but it is kind of like something that is limited in the total size of the systems that we actually can calculate and in the timescales that we can actually simulate. On the other hand, in particular, all of these kinds of questions in the area of energy conversion or catalysis very often ultimately require to really go to macroscopic scale. And that is something where now what we need to do in general is something that we need to couple quantum chemistry or electronic structure theories to different kinds of theories that we have that operate more on these kinds of scales. At the mesoscopic scale, this is particularly thermodynamics and statistical mechanics. And then at a macroscopic scale, eventually it doesn't make any sense to resolve individual atoms anymore. And so we would, for example, then resort to continuum mechanics kind of theories of computational fluid dynamics. And these sorts of coupling approaches of how one would actually integrate these different kinds of theories, this is what is called multiscale modeling. There are different ways of how one can do it. Conceptually, the two most prominent ones are so-called concurrent multiscale modeling or sequential or hierarchical multiscale modeling. Concurrent typically means that it is more like a spatial multiscale modeling, so trying to bridge length scales. It means that we're trying to resolve our total system at different levels of resolution. So we would, for example, have one smaller area of our total system that we describe with a higher level of theory, for example, in electronic structure theory. And then we would treat the rest of the system at a more coarse-grained kind of level, for example, an atomistic force field or so. And then the question, of course, is how can we embed this or integrate these two kinds of calculations? In sequential or hierarchical kinds of schemes, what one rather does is one uses one theory first independently and it gives some output. And then that output becomes the input of another kind of theory that then can treat different lengths or time scales. So it's really here more like depicted in this graph that we sort of like pass information from one simulation to the other. Very often sequential or hierarchical schemes are more used, for example, for the time domain to access longer time scales. As I already said, one important part of this is also coarse graining, because imagine that we would have the perfect supercomputer scalable to full extent, and we have a program like FHI-aims that is perfect, and it would allow us to maybe even do a calculation where we could do a density functional theory calculation for 1 cubic centimeter of material. Imagine that we could do that, and maybe even many of these sorts of things. We would basically die in the information that is provided. Because at the end of the day, the importance is also in a physical modeling is that we have to condense the really relevant information out. And that is called coarse graining, in sort of like that we really try when we go to larger scales that we only pass that kind of information forward that is really relevant for these larger things. So typically coarse graining goes through a sequence where first we do an electronic structure calculation, then pass this sort of like coarse grain out the electronic degrees of freedom to go to an atomistic scale kind of modeling. And then we start to sequentially coarse grain out different atomic degrees of freedom. So we would go to pseudoparticle approaches or lattice approaches, and then eventually to a continuum. Things that how one could actually do this kinds of things is, of course, a logical one coming from first principles is that one would think, oh, let's go bottom up. So we start with first principles and then coarse grain to go basically to larger scales. But that is something that is maybe more natural to us as natural scientists, physicists, or chemists. For example, in the engineering world, they very often come from macroscopic engineering kind of models and then try to introduce increasingly sort of like detailed information into this. So these are then typically so-called top-down approaches. Ultimately, we might actually need loops or so where we coarse grain and then introduce again more detail, etc. But this is not where the field currently is. We're very often very happy if we can only just close the gaps and bridge between the different methodologies. The big difference between going the way up or down is also the difference between predictive quality modeling and empirical kind of modeling, here illustrated by this sort of cartoon. As you have heard in the tutorial series up to now, we put a lot of emphasis on actually first principles kind of calculations. Why? Because what first principles means typically is that we become predictive in quality. We can do calculations, we can do modeling and simulation and arrive at predictions that are independent of experiment. Not that we would sort of not like experiment or we would distrust it, but it's basically with a predictive quality theory, we can provide complementary information that may not be that well accessible to experiment, and we can help experiment and work together hand in hand with experiment to solve problems. And this huge advantage of first principles theories is sort of like a complete difference to more empirical theories, which are theories with very often with many free parameters, and then one simply fits them to experiment. One very often has to be very careful in the latter kind of approaches that one does not basically only get out what one had put in terms of these parameter fittings that one had done in the beginning. Why is this important here? Well, the importance is if we do multi-scale modeling and we now start to interface first principles kind of calculations, electronic structure calculations with other kinds of theories, we have to be very careful in how we do that. Because if the way how we achieve such couplings, either in concurrent approaches or in hierarchical approaches, if that involves dozens of free parameters that we can only determine by fitting to experiment, the question is, why did we put so much effort into the first principles calculation in the first place? Because with all these additional free parameters that we fit to experiment, we can probably fit an elephant, and we would not maybe have needed the first principles calculations in the beginning at all. So if one does such kind of multi-scale modeling approaches, one has to be very careful about error propagation. One uses sensitivity analysis to make sure how errors sort of like propagate through the different kinds of scales, and then how additional parameters, how we can determine them with at least a minimum amount of empiricism, and how sensitive we are to these maybe necessary empirical kind of parameters. With that general intro, again, just a brief recap. I don't really want to show that much more than this one slide. I trust that from the tutorials that you have heard up to now, you're now fully versed with this. So electronic structure calculations basically solve the Schrödinger equation, very often the time-independent scalar relativistic Schrödinger equation, either with a quantum chemistry ansatz, which is doing sort of like the many-body wave function, or with switching to the electron density as the main variable, and this is the density functional theory, with very often these very simple solution in terms of these local or semi-local functionals that you have already heard about in this tutorial series. What we will focus on today for the lecture is now in particular one coupling approach, which is called ab initio thermodynamics. You can view this quite generally as a kind of concurrent approach. We use first principles calculations to describe some small part of our system, and we basically couple this on a thermodynamic level to reservoirs that are no longer atomistically described, that are sort of coarse-grained to just being a reservoir. But by doing this kind of coupling, we achieve a description of much larger and actually quite complex systems. This approach was developed and pioneered by Matthias Scheffler and his co-workers roughly in the 1980s in its first conceptual ways. It is very general, originally has been developed and applied in the semiconductor world. It then made its way into catalysis, into electrocatalysis. It's a very general approach of how we can couple first principles calculations to thermodynamic considerations to extend, in particular, the length scales that we can address. By definition, of course, only an approach that works on the length scales, because thermodynamics means that we average in this way or get the system properties after an infinite amount of time. So there's no temporal information in this. I will show this slide later on again to explain to you more what this approach is. This is really just to initially motivate, first of all, why we need to extend the realm of quantum chemistry calculations, but then also that in today we will particularly focus on ab initio thermodynamics as one very prominent concurrent multiscale modeling approach that is used nowadays quite routinely, actually, in many areas whenever we do first principles calculations. To provide the ground for that, let me first recap a little bit essential thermodynamics and statistical mechanics, just to put us all a little bit on the same page, because as the name ab initio thermodynamics says, it is a thermodynamic approach, and so we definitely need to know a little bit about thermodynamics. Now, you will all remember from your undergraduate lectures that in principle we have sort of like these 4 important potential functions in thermodynamics, which are each minimized in specific kinds of representations. So different sort of like Tp constant or Tv constant, etc. You will also remember is that if one takes the total derivative of each of these potential functions, because they have the dependence on these 2 kinds of quantities, so like you can come to these very famous kinds of first derivatives. And if one now takes the mixed partial derivatives and understands that mixed partial derivatives are equal, you recover many, many different laws that originally in classical thermodynamics were first derived empirically, but are basically, if one now understands, it's a pure math manifestation of mixed partial derivative. Some quantity that is particularly important in the context of ab initio thermodynamics is the so-called chemical potential, which is basically the Gibbs free energy per particle for a homogeneous system. And in a very tangible picture, you should imagine the chemical potential as the cost to remove a particle from your system. Very much like to explain this with the idea of Lego boxes. Imagine that you have a Lego box with different of your individual Lego stones of different colors. And for example, now you would like to add to your system a red Lego stone. Let that be a red atom, a little bit more physical. Now, if in your Lego box there is no red stone, it costs you basically an infinite amount of energy in order to add such a red stone to your system, because there is simply none. That means your chemical potential, and that was in the nomenclature that I will use in this lecture, will be minus infinity. Now, if I have more and more of these red Lego bricks in my box, it will be exceedingly easier to add these kinds of things to my system. And that means that the chemical potential of these red Lego bricks will start to increase from minus infinity to something that approaches eventually 0 and then becomes even positive. So the chemical potential simply reflects how easy I can actually add a particle to the system, or then the opposite, also like the opposite sign of the chemical potential means the cost to also remove it again. So far for thermodynamics. Statistical mechanics comes from this completely different angle, that you will know that the system will flow through its huge phase space. Why is that important? Well, because in classical thermodynamics, we have all these sort of like equations that link the different potential functions, etc., with each other, but we have no means to actually compute it specifically for one given system. And this is where we need statistical mechanics, because we need the partition function as the gateway to actually do that. And why? Well, the partition function of a system is something that is a Boltzmann-weighted sum of all possible states of the system. And this is where we can actually input atomistic information about our system into this, as I will explain in a second. But why is this important? Well, because once we have the partition function, we have this important equation here that then links the partition function to the free energy, the Helmholtz free energy in specifics. And that is the important gateway, because through the partition function, we can actually compute through this equation one of the potential functions, the Helmholtz free energy. And once we have that, then we can use all of the thermodynamic equations to get the other potential functions. And this is why this is so important, because it allows us through this to basically channel the atomic scale information into classical thermodynamics. And then all the standard equations of classical thermodynamics help us to get basically all other kinds of thermodynamic properties that we would in principle be interested in. Another important thing to remember is that the partition function basically decouples if there are degrees of freedom that are decoupled from each other. So, for example, a very frequent approximation is that the electronic degrees of freedom decouple from the nuclear ones. This is the famous Born-Oppenheimer approximation. And that would mean that the system states, or the partition function, would basically simply become a multiplication of subpartition functions regarding the electronic and the nuclear degrees of freedom. Similar decouplings operate for rotational and vibrational degrees of freedom. If we then see that we're operating with the logarithm on the partition function, you see, of course, that if something is multiplicative in the partition function, it is simply a sum, an additive in terms of the free energy. Now, one important thing is, of course, that this is also classical theories, whereas in reality, we have, of course, the problem of indistinguishability between different atoms. And that means that one has to introduce a sort of like a correction in there because it's indistinguishable particles in other way, because otherwise we would run into a general problem. So with this recap, let's do one simple exercise here to basically compute the free energy of an ideal gas. And so like we would write down the total partition function as our first target that we want to compute in the way how we've just described it. And we would differentiate, of course, the different degrees of freedom that we have. So the nuclear degrees of freedom, electronic, translational, rotational, and vibrational degrees of freedom. Now, how can we compute these different parts here? Well, first of all, typically in chemistry, we're not messing around with the nuclear degrees of freedom unless we're in nuclear magnetic resonance. And so this is a constant, basically, and then in all the differences that later on we want to analyze, it basically drops out. So we don't have to worry about it. That, therefore, then, of course, yeah, we apply the general definition. If we want to, for example, get the chemical potential, we realize, the ideal gas is a homogeneous system. So the chemical potential is simply the Gibbs free energy per particle. We introduce the thermodynamic definition of the Gibbs free energy to get a relation to the free energy. And then we use the famous Boltzmann equation to basically get the relation to the partition function. How can we now compute these individual contributions here that we have? The electronic free energy is basically now the sum over the typical excitation energies that enter in here. Typical electronic excitation energies have sort of like energies of the order of fractions of electron volts or even electron volts. That's much larger than kT. So in this Boltzmann weighted sum, sort of like higher excited states contribute very, very little. And so typically it suffices to essentially focus on the electronic ground state as the predominant contribution to this electronic partition function. The only difference maybe being if we have some spin degeneracies in the ground state. And so if you want to compute the electronic free energy of an ideal gas, what we basically just need is the electronic ground state energy, which is in thermodynamics called the internal energy. You know it as the total energy in the preceding tutorial series that we had. So this is the quantity that we compute with density functional theory. The only caveat that we have to keep in mind is that there is also, of course, again, the problem that in principle there are 0-point energies. Remember again, we're now using, in the sense of a concurrent model, we're using input from a quantum mechanical theory, quantum mechanics, and we're putting it into a classical theory like thermodynamics. And that is intrinsically a little bit problematic, and that sometimes we have to cheat. And so 0-point energies is, of course, something that we have to add to the internal energy to make everything consistent. Now, second contribution that we have is the translational free energy. Here we basically use standard equation for a particle in a box of length given by the box. And then we let the length go to infinity. And you arrive at this equation. I'm actually quite sure that most of you have derived this equation in their undergraduate statistical mechanics course. You see that the only input that we really need to know about our gas is actually the particle mass of its constituent molecules. Now, If we move on to the rotational free energy, we use a similar approximation. Here we use the rigid rotator equation, and you see again that the actual input that we need about our gas is quite simple. It's rotational constants. Eventually, now we move to the vibrational free energy. We use the equation for the quantum mechanical harmonic oscillator. We cheat again, classical theory, but we use the energy expression of a quantum mechanical harmonic oscillator. And again, the input that we need are the vibrational modes of the molecules in our gas. And I think you have actually already computed vibrational modes in this tutorial series. So it's basically setting up the dynamical matrix and getting the second derivatives of the total energy with respect to positions of atoms. And then you can basically also get these vibrational modes. So if we put this all together, if you want to, for example, compute the free energy of an ideal gas of oxygen, for example, the only real input that we really need are these 5 quantities in here, which partially we can look up in tables, so they're obvious, or we can compute them with DFT, for example. Same for CO. And then we can write our chemical potential as the sort of like the total energy of our system plus some temperature and pressure dependent part. Remember, the chemical potential is in the constant T and P regime. So this is something that is a function of temperature and pressure. And here you see the outcome. You see actually the accumulated individual contributions to the total chemical potential as a function of temperature, here to the left for oxygen, to the right for CO. And you see sort of like that the dominant contributions to this is actually the vibrations and the translations in here. The solid lines are really just computing these analytical expressions that I've shown you on the preceding slides and adding these quantities in here to determine them. The crosses, on the other hand, is an alternative approach where you basically get this from thermochemical tables where this kind of information is actually tabulated for many, many gases. And you see that on this kinds of scales, this is essentially the same, even though our expressions, analytical expressions, are, of course, approximations because we're using a rigid rotator or we're using an harmonic oscillator. Now, why is this, or let me then now move, this is for ideal gases. The opposite would be a solid. In solid, we do again the same kind of game. I'm directly starting with the Gibbs free energy and we write it as these different contributions from our different degrees of freedom, so translations, rotations, vibrations, configuration, entropy, and the PV term. Here's a little bit different now because whereas in ideal gases, the translational and rotational free energies were huge contributions for a solid. This means, of course, the translational free energy and the rotational free energy of the entire block of solid. That's something macroscopic, and since this scales with 1 over the mass, this is something that is essentially 0 for us. PV typically varies little for many, many solids because by changing the pressure, the volume typically doesn't change too much, at least not appreciable on the normal pressure range that we're interested in. So this is again a constant and we can typically drop it because in differences it will cancel. For configuration entropy is a troublemaker, and I'll come back to that in the lecture. And then we have the internal energy and the vibrational free energy. Again, we compute it as for an ideal gas. So internal energy is basically what we could compute with DFT. Now for a solid, for example, typically in a periodic supercell. And the vibrational free energy is not the individual vibrational modes as for a molecule, but this would be the phonon band structure of our solid that we compute. Typically, we don't need absolute Gibbs free energies. We typically need differences. I'll show that in a few slides from now. And in these differences, many things actually cancel. And so in these differences, we can also very often live with very simple models for the vibrational free energy. So just simple models like the Debye model or the Einstein model for a solid, you probably know from your solid state physics lecture. And so in solids, these differences of Gibbs free energies can very often, to quite some good degree, be approximated as the difference simply of the total energies and then the differences of the configuration. And just to give you a very simple example, it's a famous example. It's in one of the very first pages of this famous solid state physics book by Ashcroft and Mermin. Let's show a little bit how this coupling of first principles energetics and thermodynamics helps us with to get really interesting results. This here would be, for example, to compute the concentration of point defects in a solid. And it definitely has to be something that is a purely entropic effect, because in a normal solid, it will always cost energy to create one vacancy. So normally you wouldn't have them, but because of entropy, there are actually some at finite temperatures. And the question is, how many are there? Yeah, we can make a very simple model. Let's simply take a simple cubic crystal, doesn't really matter, for the differences, which has capital N kinds of signs, and we want to create small n numbers of point defects. And so the total energy of our system, internal energy, we can basically write as n times the energy that it costs to create such a point defect. The configuration entropy is something that we can actually simply enumerate here. It's very simple, because if we move with the first, start with the first side, or in total we have capital N sides, we have basically for the first defect, we have capital N possibilities to create that point defect somewhere. For the second point defect that we want to create, we have now n-1 sides, because we have already one side occupied. For the next point defect, n-2, etc. And this would sort of like continue until the number small n of vacancies that we want to create. We have to renormalize that though, because it doesn't matter in which order we create these point defects, because they're all identical. And so we therefore have to sort of like divide by this number, and we arrive at these famous factorial kinds of expressions that I'm quite sure remember from statistics. If we now minimize the Gibbs free energy, which would then, as a function of the number of point defects, which is sort of like giving us this point concentration, then in equilibrium. Forget about the PV term again, as I already motivated. We use the famous Stirling approximation. You arrive at this very famous equation, which says that the point defect concentration, so the number of point defects per sites, is simply this exponential of this Boltzmann expression of the cost to create an individual point defect. And you see that at any finite temperature, you will also arrive at a finite point defect concentration. And you see, if we can basically now do one DFT calculation to get a good approximation to the one individual point defect concentration, by plugging it into thermodynamics, we can evaluate or determine an expression for how many of these point defects are there at a finite temperature in a macroscopic crystal. And that is sort of like the power of this concurrent multiscale modeling approach of Initio thermodynamics, in using first principles quantities, plugging them into thermodynamic formalisms to arrive at valuable kinds of expressions. Now with that, let's become a little bit more catalytic and move to surfaces. And let's first, for example, start with a simple gas phase, so maybe just a gas environment of oxygen, and then a context that is suitable for this in terms of applications would be oxide formation of metals. This is something that also for catalysis is very important, because many catalysts are transition metal catalysts. And we very often have, for example, studied them in ultra-high vacuum very accurately on the atomic scale in surface science approaches. The problem is that in reality, catalysis takes place at much different operation conditions, so at ambient pressures and typically elevated temperatures. And it could simply be that these metal catalysts that we are using in catalysis do no longer stay metallic, but they actually start to oxidize, either forming really full bulk oxides in very oxygen-rich environments, or maybe in between, they would just form thin films of oxides, something that we call surface oxides in the jargon. Now, how could we evaluate that with first principles? An important thing basically is to realize that in any real gas phase, our surface is not really just seeing one oxygen or so, but it actually is bombarded by oxygen. You can get this from kinetic gas theory. You may remember this famous equation of the impingement rate that you have on the surface. And if you plug the typical numbers in, you see that every atomic site on a metal surface is typically actually hit by a gas phase molecule about 10 to the 8 times per second. On the other hand, if we do it with straightforward, for example, ab initio molecular dynamics, where we use our DFT power to really create an atomic scale movie, we at maximum can maybe do individual oxygen molecules impinging at the surface, and then doing this over very sort of like short times. This is a stone old example of a time when Jörg Behler was still a PhD student in Matthias Scheffler's group in the theory department of the Fritz. But it sort of like by now, of course, computers have become much, much more powerful, but the conceptual problem remains. While those days for this trajectory, we would essentially wait for 1.5 months to come out. And nowadays, maybe with massive parallelization and more powerful supercomputers, you can squeeze this down to a few hours, but it still doesn't solve this problem that essentially you can maybe go to nanoseconds or a little bit longer, but not anywhere else. And definitely not to sort of like really mimicking this true gas phase bombardment and then really seeing the slow time scale of oxide formation, which might take actually milliseconds, seconds, hours, depending on the conditions. How can we do that differently? Now that's the idea of ab initio thermodynamics. The idea would be, well, what we can calculate with density functional theory would be maybe a finite small cutout of our surface which we would describe in a supercell. So we would set up a slab model, and then we would be able to do an individual DFT calculation. And the idea of ab initio thermodynamics is now to say, well, this is, of course, in principle, we would do this in vacuum because we would fill up the supercell with vacuum on top of the slab and at the lower end of the slab. But what we can do is we can now use thermodynamics to couple this and assume that there is equilibrium of this part that we describe on the DFT level with chemical potentials or thermodynamic reservoirs that on the one hand represent the infinite gas environment and on the other hand represent the infinite bulk environment. And so the general approach, generalizing this, is that what you use in ab initio thermodynamics is that you separate your system, overall system, which might be very large and very complex, into subsystems, and that some part of these subsystems or some of these subsystems are basically then homogeneous reservoirs, which are very easy to compute. And you calculate these properties of these subsystems separately, which definitely always makes it cheaper, and you connect them by applying equilibrium between these subsystems. Already mentioned, the big problem is, of course, there is no temporal information. This is all under the equilibrium assumptions, but at least you learn something, so to speak, about your system properties after infinite. What would be now a central thermodynamic property that we would want to calculate with this? Well, it is the so-called surface free energy per area, or the surface tension. In order to understand that, it's important to remind oneself that a surface can never be alone. Even though a solid, when it's surrounded by a gas phase, we typically just think of the surface. But that's not true. There's two sides to it. The other side is simply the gas phase environment. Or if we're solid liquid, it's the liquid environment, or solid solid, it's another solid environment. So we typically have two different kinds of phases. And if we now say, what is the total Gibbs free energy of a system like this, which is contained of two phases, it is not simply just, so to speak, the Gibbs free energies of these two different phases individually, but there's typically an additional energy cost which is connected to this interface area that we have here. And it is natural to assume that this cost scales with the total area of the interface, and this prefactor, that is the so-called surface tension then. And if we now reorder this equation, we arrive at this other famous equation here, which now gives us this surface tension, or the surface free energy per area, as sort of like the total Gibbs free energy of our system minus the sum of sort of like these homogeneous systems. And this is homogeneous systems. We can, as you know, always describe them as n times the chemical potential. And now we play exactly the game of computing these Gibbs free energies that we have played before, and we exploit the different equilibria that we have. So that is the equation that we want to evaluate, for example, in the context of a surface in equilibrium with an oxygen gas phase and in equilibrium with a metal bulk. So we have the Gibbs free energy of our total system. We have to subtract and the number of oxygens that we have times the chemical potential of oxygen. And the same for the metal atoms. And what we now do is we use the reservoirs. Well, if we assume that this surface here contains oxygen, likely in oxide formation, but we say that it is in equilibrium with the surrounding gas phase. And remember, if a system is in equilibrium, then the chemical potential is everywhere the same. And so this means that we can basically say now in this equation here, even though we want to describe this region here, can compute the chemical potential from the surrounding gas phase, which is just the one from the ideal gas. That's the exercise that we just did. We use another equilibrium because we say that this surface fringe here is also in equilibrium with the underlying bulk. And that, of course, means that the chemical potential of the metal atoms is the same everywhere, and is the one simply as the one that we have in bulk. Remember, we now write for the bulk basically this approximation that we have derived before. And if we then even say, make it simpler and forget about the vibration of free energy and even the configuration of free energy for the moment, dV is again negligible, this general equation becomes something very simple and something very accessible to DFT calculations, because it is basically now here, the total Gibbs free energy, we instead have now just the total energy of our surface lab. So that's just the total energy that we would get from calculating one slab in a supercell by DFT. We have to subtract m times the total energy of a bulk unit cell of our metal, and then we have the chemical potential of oxygen. How can we use this now? Well, for example, in oxide formation, what we could do or think about different sort of like configurations and structures that the surface might possibly adopt. Here's an example of oxide formation on a palladium 1O single crystal. And we would use as a reference the clean palladium surface as a function of the chemical potential. And now we're only plotting this delta chemical potential, so the temperature and pressure dependent part, which remember we can analytically also basically convert into dependencies, for example, as a pressure dependence, as a fixed temperature. Delta chemical potential is just a summary summarizing the two-dimensional dependence on both temperature and pressure. As a function of this delta chemical potential, the clean surface free energy does not show any dependence because, well, if I have no oxygen around, this NO is 0, and then this equation basically simplifies to a constant sum. And here we're even using this as a reference. We subtract this surface free energy of the clean surface, so this is our 0 reference. Now, you can say, well, but maybe obviously if we have oxygen in the surrounding gas phase, maybe at first there are some oxygen that absorbs at the surface, for example, in terms of like such an ordered P2x2 overlayer here. That is a structure that we can compute with DFT, and we get the total energy of it. And we put it in here. Now, what we now have, of course, now we have a certain number of oxygen atoms per area. And so this will now depend as a function of this delta chemical potential. And it will actually make, as you see here by the negative sign, that makes the surface free energy smaller with increasing oxygen content in the gas. And that makes sense. Remember the chemical potential in terms of this Lego brick analogy that I told you. What does it mean that if a chemical potential becomes more and more sort of like positive? Well, it means there's more oxygen around. You see this here, there's increasing pressure around. It's therefore increasingly simpler for the system to acquire oxygen. So the higher our chemical potential, the more oxygen rich our gas phase, it will actually cost less to create such a surface with oxygens because there's more oxygen around. And therefore, the surface free energy of any oxygen containing structure will actually become smaller with increasing chemical potential. And the slope of this will be basically the number of oxygens per area. So if we move to a structure that has more oxygens, for example, such a surface oxide film, which has more oxygen per surface area, that slope will be steeper. And so we can do this, for example, now, and we can compare all these different kinds of lines. And what you see is, of course, that in thermodynamics, well, the structure that minimizes the surface free energy, that will be the one that is sort of like the most stable one. Remember, thermodynamics always minimum of something. And if we now do this for a number of different kinds of structures, what we can read of here would be that under oxygen gas phases that would sort of like match this area here, which is sort of very little oxygen around. Of course, yeah, then the clean metal surface will be more stable. We increase the oxygen content in the gas phase, eventually the add layer will become more stable, this P2x2, then the surface oxide. And if we eventually cross this kind of line here, this is where bulk oxide formation will start. It has an infinite number of oxygen atoms per area because the bulk oxide extends infinitely into the Z direction, and therefore the slope is minus infinity here. And you see here, now what we can do is we can discuss what is the oxygen content of our surface and what will form in different kinds of gas phases. And the only thing that in practice we have to do is a few handful of DFT calculations of these different surface configurations. And that is the power of ab initio thermodynamics. Remember, in contrast to an ab initio molecular dynamics, where we would have to actually evolve a long trajectory and we would still maybe only go to nanoseconds and you would never see this. See, this is the power of concurrent multi-scale modeling. If we use the appropriate kind of thermodynamics, then we basically can get a lot out of our DFT calculations and we can suddenly make contact to real life. And that it actually is not too bad. This was work here, for example, very early work of these kinds of applications, we compared to experiment. You can basically plot, so like what is the most stable thing that forms in this here, not only as a function of chemical potential, but instead really resolve it as a function of temperature and pressure. And so you get what is then called a surface phase diagram. And that would be the prediction of our ab initio thermodynamics. So here we have the clean surface, then the add layer, surface oxide, and the bulk oxide. This is data from experiments, surface X-ray diffraction and Lundgren and co-workers at the time. And you see, of course, it doesn't really match completely. There's several kinds of reasons. Well, the first thing is the experiment is typically creative. Mind that when you work together with experimentalists. So the true data that they have is marked here by these individual points. And of course, what they then do is they draw a surface phase diagram with these boundaries between different surface phases a little bit according to creativity. So that this line is actually exactly here. If the only data points that you have is here, 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 and here, there's room for freedom, right? And so that has to be taken into account. But nevertheless, there are, of course, differences. And this definitely, of course, now hits us at our typical weak point, and that is the DFT functional. So with the semi-local functionals, of course, we're not getting a total energy that is exact, but very approximate. And unfortunately, what this typically translates in that we have uncertainties of the order of 100 Kelvin, maybe in orders, 1 order or 2 orders of magnitude in pressure. And so, yeah, these exact position of these boundaries are wrong. We compute them with DFT, other DFT functionals, they shift basically. The overall structure doesn't change, but the exact transition points shift. But so one important difference is that there's something that does not match at all. And this is basically that up here in the experiment, they basically see always still the surface oxide, whereas in reality, we would predict always the stability of the bulk oxide. That is now also being very careful in what ab initio thermodynamics can do for us. This is thermodynamics versus kinetics, right? So we predict the system properties after an infinite amount of time. What they did in experiment was they exposed the surface to an oxygen gas phase and then they waited for a certain time, but they had only that much beam time. And so under these conditions, relatively low temperatures and very high gas phases, simply in the time of their experiment, the bulk oxide could not form yet. There are actually a few points like this one here, which originally was the surface oxide, but then they, because of our complaints, they remeasured and waited longer. And then suddenly, after a longer time, they saw the diffraction patterns of the bulk oxide. And so it's basically in here, you're in a kinetically inhibited regime. And that is on the one hand, a limitation of experiment, but on the other hand, is something that is one always has to have clear in mind when one does ab initio thermodynamics, is that we do thermodynamics, right? So we cannot cover kinetic effects like this. So this is a very simple recipe of how you can get into these phase diagrams in surface catalysis. In thermal catalysis, they're really called phase diagrams. In electrocatalysis, they are called Bourbet diagrams and they have different quantities. So in thermal catalysis, the two parameters representing the operation conditions is temperature and partial pressures. Whereas in electrocatalysis, it's the applied bias and the pH, for example, if you are in aqueous electrolytes. But one can set the same kind of ab initio thermodynamics up for electrocatalysis as well. I don't have the time to do that today, but in principle, one can. And so with ab initio thermodynamics, we can get these kinds of phase or Bourbet diagrams. You can also extend this, for example, to predict the particle shapes. This exploits another thermodynamic construction, which is called the Wolf construction. And you basically just need the surface free energy in all low index kinds of directions of your solid. And it's a graphical approach in a sense, and that then predicts the particle shape. And if we compute, therefore, the surface free energies with ab initio thermodynamics for many different facets and put this into such a Wolf construction, we are, for example, also in the position to predict equilibrium nanoparticle shapes, which is, of course, now getting very powerful in terms of catalysis kind of modeling. But up to now, we were all in a gas phase that is really only composed of one component, and that's not catalysis. Because in catalysis, we always need at least two kinds of reactants. Take a very simple reaction like the CO oxidation here, it would be oxygen and CO. And well, the question is, how can we do that? And a very straightforward generalization would be to say, before we used ab initio thermodynamics to have our surface in equilibrium with the chemical potential of the surrounding gas phase. But if we now have two species in the gas phase, why not say that this surface is in equilibrium with these components of our gas phase? This would be a very straightforward kind of approximation. It doesn't work though, that straightforward as it is, because you might have heard them saying that catalysis is all about kinetics, isn't it? And that here translates to the fact that if we really apply equilibrium then through all subsystems that we have here, so the reservoir for oxygen, the reservoir for CO, and our surface, then what we immediately would get is that all the products here, CO2, would be more stable. Remember, catalysis cannot change the thermochemistry, the thermodynamics of our thing. The products have to be thermodynamically more stable under the operation conditions than the reactants. That doesn't hold, even a catalyst can't help. The only thing that the catalyst does is change the kinetics. And so we have to do a little bit of a more sort of like cruxed approach, which we termed, Matthias and I termed it constrained equilibrium at the time. We basically say that the surface is individually in equilibrium with the reactant gas phases, the chemical potentials, but that these chemical potentials are not in equilibrium with each other. Then we can play the same game as before. Now the surface free energy is no longer just a one-dimensional function of one chemical potential, but also the one of the other chemical potential. And what were lines before are now planes. And that's becoming a little bit more complex to look at. But remember, we are typically only interested in what is the lowest lying one, because that is the structure that is in the most stable one, predicted to be more stable. And so it corresponds to actually taking a look from the bottom up into here. And again, then we arrive at surface phase diagrams like this. And something that we realized at the time was here, I don't have the time, I don't want to go into the full details of all these different structures, but all these structures, basically everything corresponds to one DFT calculation. You put it into your surface ab initio thermodynamics, and you get such a phase diagram like this. And then you can sort of like make contact to experiment, which is sort of like around here, 1 bar, at 300 and 600 Kelvin. So this would be typical experimental working conditions for technological catalysis. And you can then make statements about what is the structure and composition of your catalytically active surface. The problem is that we're not that ready yet, because remember what I said at the time, let's forget about the vibrational free energy and the configuration of free energy for the moment. So we simply just dropped it without any justification. And what problems does this make? Well, very importantly, first of all, configurational entropy. Remember, we have sort of like we said, okay, for example, we have one structure with a clean surface and one that is an oxygen containing one as a function of the chemical potential. What does this mean in terms of our coverage of oxygen at the surface? Well, in this particular example, it translates from a clean surface, you have no oxygen at the surface. And then suddenly here where the lines cross, now we would say this structure is more stable and this structure has a quarter of a monolayer of oxygen on it. So it's like this. So we have a step function. And immediately your alarm bells ring. Nobody knows, step functions make no sense in physics, because this would basically then say if we increase our temperature, for example, just a little bit to change the chemical potential, we would suddenly have, with an incremental temperature change, a huge change of oxygen coverage on the surface. And that this is wrong has actually to do with that we have neglected the configuration of the energy. And if one has no lateral interactions on the surface, one can again enumerate this. It's very similar to this example that I've given you for the bulk point defects. And if one evaluates and minimizes this, one arrives as even an analytical expression for the oxygen or the coverage of oxygen at the surface as a function of the absorption free energy. This is called the Langmuir absorption isotherm if you assume that there are no lateral interactions between the oxygens. And if one plots this, you see that this term now would resolve this discrepancy in that it basically smears out this phase transition. So rather than having sort of like, we're here more stable with the one phase and here more stable with the other, what you have is a gradual depopulation of the one phase and the population of the other one. And the width is, of course, proportional to temperature. And so in principle, if we even cannot compute configurational entropy explicitly, what we learn is, so to speak, is that if we draw these phase diagrams, we have to be careful about these phase transitions or these boundaries here. First of all, as I said already, they can shift strongly with the DFT functional, so the absolute position is also not that certain. But generally, also one would think that they're a little bit smeared out. Sometimes we draw them, therefore, as these kind of like wide intermediate regions in which sort of like both phases are a little bit prominent. Fun fact is that typically, if you plot the experimental operation conditions on top of this, you will see that they are basically close, or they are lying on top of such phase boundaries in here. And so one can actually see, in general, catalysis as a phase transition phenomenon. Typically, a good catalyst is a catalyst where your surface wants to undergo some sort of like a transition to some other kind of phase, and it is intrinsically a little bit unstable, and that creates a lot of dynamics, and that generally is good for catalysis. This is super oversimplifying, but roughly that is something that definitely holds in general. Again, beware of kinetic effects. We had them already an example with the oxygen, but also here in these phase diagrams, here we cannot compare to experiment, but you can, for example, compare to a dedicated kinetic model, which evaluates the kinetics. And again, you will see that parts of your phase diagrams will change simply because, we are only doing ab initio thermodynamics in general. So one has to be very careful with reading not too much into such kind of phase. And then as a last thing, something that is super important, because I really see this done very often in a wrong way in publications, beware of the configuration of sun. What does that mean? Imagine again a simple example. We had such a situation here. We have calculated a number of surface structures and configurations. They have given us all these different free energy lines as a function of a chemical potential. For example, a clean surface, B2/2 in the surface oxide. We've already learned that if we would consider this really as a true temperature, at low temperatures, of course, there would be a sort of like configuration and free entropy would basically smear this out a little bit, this regime in here. Of course, if the temperature becomes too large, the smearing out will become wider and wider, and eventually at too high temperatures, we're of course not getting an ordered oxygen structure, but a disordered lattice gas. And here in this sort of like that, we cannot describe this without really explicitly computing the configuration of free energy. That's one problem. But imagine another problem. We have computed a number of structures here. Maybe we have come to these structures from experiment, they were seen in experiment, or we have simply by our chemical intuition or knowledge of the system, this would be structures that we think are useful. Imagine we had not known about the P2/2 structure, and we would not have computed it. Then the surface free energies would be like this, and the phase diagram that we would basically predict would be now not showing a P2/2 structure. It's not in principle the problem of ab initio thermodynamics, but it's the problem of what structures we put into it. And that is the big take-home message that I want to give you at the very end, is that any ab initio thermodynamics phase diagram is really only as good as the structures that you explicitly sampled. That is the big problem with this sort of like very simple approach to ab initio thermodynamics, in that we compute a number of structures. And then the only thing that ab initio thermodynamics allows us to do is to compare these structures that we have explicitly calculated. It will not tell us that an important structure was missing. That's not something that this approach to ab initio thermodynamics can do, but this is something the approach that Jörn will now talk about in the second lecture can do for you. And so let me wrap this up again with this slide that you have seen overall. I've only illustrated the use of ab initio thermodynamics for this sort of like surface context, but the approach that Matthias developed is much, much more general. It is basically, you can apply it to many different application areas, because the idea is of that of a concurrent multiscale modeling approach, in the sense that you describe some subpart of your system with DFT, and you can treat much larger and more complex systems by basically connecting this explicitly calculated subsystem to reservoirs in a thermodynamic sense. With it, thank you very much for your attention, and I'll be later on around in the hands-on session if you have more questions. Thank you.
Thank you so much, Karsten, for this very nice question. And yeah, the discussion is now open for questions. So you can either unmute yourself, ask questions in the chat, or use the Slack channel to ask questions.
Hi, may I ask a question?
Sure.
Hi, Karsten. Beautiful talk. I've followed your work for a long time now. I did my PhD with Andrew Rapp, so we used a lot of some of the things you developed.
Good old friend.
Yeah. So my question is, you mentioned that obviously ab initio thermodynamics is limited by the fact that that many experiments are limited by kinetics of surface formation. My question for you is, are there approaches for including surface kinetics between phase transformations of the different, surface reconstructions you find, to almost have some sort of time resolution that can allow you to see how the phase diagrams change, depending upon how long you wait till equilibrium?
Yeah. Yes, there are. I mean, you would just have to then basically switch to kinetic models. These are typically then more hierarchical models. So you set up a kinetic model, can actually be a mean field, microkinetic model. It could be a kinetic Monte Carlo kind of model or any other thing. And what you use there is that you again compute with DFT specific input that you need there. So in ab initio thermodynamics, the crucial input that, as you have seen, is the total energies of your systems, so to speak. In a kinetic model, the crucial input would, for example, be an activation barrier that you can compute, for example, with a nudged elastic band calculation with DFT as well. And so you need information about these barriers, you need information about the prefactors, and you can put this into kinetic models. The problem is that kinetic modeling is much more involved than thermodynamics, obviously, because in principle you get more out of it. And mostly what is still done in the surface area is sort of like still based on lattice models. Unfortunately, you have to assume some form of crystallinity of your surface. The reason simply, if you have crystallinity, you can exploit many symmetries, translational symmetry, etc., and that reduces strongly the amount of first principles input that you need. But on the other hand, even in oxide formation, you immediately see the limitation. Typically, oxides don't have the same crystal structure as the metal on top of which they are forming, and you have incommensurate kind of structures, or eventually you might even have amorphous regions, and that we are largely bust with the current technology that we have. But conceptually, in principle, you can do similar kinds of ideas. I mean, the conceptual idea of ab initio thermodynamics is to basically use DFT to compute some of the parameters or inputs that you need for a thermodynamic model. And in kinetics, it's the same. You use DFT to compute sort of like some of the parameters and inputs you need in a kinetic model.
Gotcha. Okay, thanks.
We have one raised hand by Mustafa. Mustafa?
Yeah, thank you. Thank you for a very great talk. I'm just curious about the phase diagram when you showed the disordered phase on the surface. Was this one actually obtained by including the actual configurational entropy in the model? And
not quite sure. Let me maybe show my presentation again. I definitely never showed a disordered phase, because to answer you directly, we cannot describe a disordered phase yet with these sorts of things. Let me see which phase. Were you looking at this phase diagram?
I think it's the slide.
Oh, you mean here at the very end? This one? You mean this?
Yes.
No. Yeah, but sorry. This would be what you can calculate with ab initio thermodynamics. And if you completely neglect configuration entropy, what you can get from this true phase diagram is basically this bottom line at t equals 0.
Right.
If you get this conceptual understanding that typically configuration of free energy smears out phase transitions, you may also be able to get from ab initio this sort of like lower part here by simply then saying, aha, I should not take these phase transitions literally sort of like as infinitely sharp lines, but sort of like as a smeared out region. And that smeared out region will become wider. Anything up here, this is only a conceptual plot. This is something that we cannot get with this way of doing ab initio thermodynamics. Of course, if you can explicitly evaluate the configuration of free energy, and you can add that. And you, for example, could do this with a cluster expansion model, for example. And then you can address this sort of thing. But what I focused on today was the simplest way of doing ab initio thermodynamics, where you basically just use the thermodynamic equations, completely neglect configuration entropy. I also didn't say much about vibrational free energy. And you just compare different kinds of structures. That's the simplest way of how you can do ab initio thermodynamics. And with this approach, you cannot access this higher temperature region. It's not possible because this is something where then configuration and entropy can no longer be neglected, and you would actually have to evaluate it explicitly.
Excellent. Thank you so much.
There is another raised hand by Raymond. Raymond?
Hi. Thank you, first of all, for the very interesting talk. I just have more of a conceptual question. In your view, to what extent are the methods of classical physical kinetics, so the Langevin equation, fluctuation dissipation theorem, that kind of stuff, to what extent are they compatible and able to be incorporated into the methods of computational ab initio thermodynamics?
Well, typically these more classical kinds of approaches, they have parameters or quantities on which they depend, which you typically cannot compute with the theories themselves, right? You can derive equations, you can make predictions, but they would, for example, scale with a certain quantity or so. And you typically cannot get that kind of quantity by that method alone. And that is typically what first principles can do, is they can maybe compute these coefficients or quantities that you need to make these general theories material specific. Because that's very often the problem that they have, is that these theories, they give us the conceptual physics, the right kind of physics actually, but they're not material specific, they're conceptual. But that's useful very often in general for us to understand a problem, but they don't help us very often in, for example, materials discovery or in true applications where it would actually make a difference to know what is happening on palladium and what is happening on rhodium. Conceptually, the same things will happen on the two kinds of metals, but maybe the one is a good catalyst and the other isn't, for example. And that material specificity you don't get from these classical theories, because they typically have coefficients and quantities in them that are the materials properties, but they cannot describe them by themselves. And typically that's these kinds of things, these coefficients is what we can compute with first principles. And if you then combine the two kinds of things, two kinds of approaches, then you can sort of like, you get all the right kind of physics out, and not only conceptually, but actually for a specific material.
Thank you.
So, are there more questions?
I'll be around later on in the hands-on session. Questions. So.
Yeah, so if there are more questions, we can discuss them also later. As Karsten said, he will be available 1 hour after, also 1 hour after the talk of Jan for discussion. Maybe some questions come up with some formulas you encounter during the tutorial, so he will be available as an expert. So then I'd like to thank Karsten again for this very nice talk, and then I would stop the recording.